Hello, and welcome to your statics video on how internal forces will vary along the length L. So here we're looking at a relatively common beam. It's the simply supported beam that has a pin at A and a roller at B. And so we know we're going to have an AX and an AY at A and a BY at B, and we see that on our free body diagram. This beam is loaded with a uniformly distributed load. Remember, we said the symbol of that is W or omega, and I use W. And that is a load per unit length. So 10 pounds per foot, 20 newtons per meter. So every time you go over a foot, you're adding an additional 10 pounds, or every time you go a meter, you're adding an additional 20 newtons, right? It's a load distributed. The load is distributed across the length of the beam. And so we know that it's hard to work with distributed loads to do our statics, and so we know we can turn it into a resultant, aka an equivalent load. It's the area of the load, so that would just be W times L. And that's our resultant R that we see there on our free body diagram, and it acts at the centroid of our distributed load, which in this case would be right in the middle or at L over 2. And so you could do your equations of equilibrium, but we can also use what we know about symmetry and by observation. Since there's no external X force, AX must be equal to 0. And because this is symmetric and the total resultant or total load of W is W times the length, since it's a load per length. So we have WL, and so both AY and BY would be WL over 2. But now what we want to do is we're like, okay, we've learned about these internal forces, an internal shear, an internal normal force, an internal moment that you could have on your beam, and we even defined the positive sign convention. So if I show my internal shear on a left side of the beam, it's going up for positive, the moment is clockwise, and the normal force is tension, or to the left. If I'm on the right side of a beam, or I've cut and exposed a right face, then the normal is still tension, but now it's pulling to the right. My shear positive is down, and my moment is counterclockwise. And so we could actually find out what is the internal shear, what is the internal moment, and what is the internal normal force at any location we want along the length of the beam. And so let's say we're going to look at points 1, 2, and 3 that are shown on our free body diagram, and those are just at the quarter points, L over 4, L over 2, and 3L over 4 as we measure from A. So if we wanted to go ahead and do our first cut, we can draw a little green line at 1 and remind ourselves we're going to do cut 1. So as I do cut 1, I'm still drawing W, right? That's really important that I draw that W value, but I can find the resultant of W, but this time, this is important, the resultant is not WL, because we only have a length of L over 4. So now my resultant is WL over 4, still acts in the middle of the shape I have there, but that means it's now acting at L over 8 from A, or L over 8 from the cut end. And I'm still going to have my support reaction AY, the WL over 2, that was going to act at the left end there. And when I exposed my internal shear, moment, and normal force, I drew them in the positive sign convention for the right side, and I gave them all a subscript 1, since this is cut 1. And once I have this all drawn, I can do my equations of equilibrium. So forces in the X is going to give me that my normal force is 0. Summing forces in the Y, I'm actually going to find that my internal shear, I get a positive answer, and it's WL over 4. And then my internal moment, I'm going to go ahead and take moments at the cut. So because I drew a resultant, I can have the WL over 4 times its length from the cut, L over 8, going in a positive direction per my chosen sign convention for that equation. My WL over 2 is L over 4 from the cut going a negative direction plus my M1 moment. And so I'm going to get that the internal moment is 3/30 seconds of WL squared over 2. And I assumed positive, and I was correct. I said WL squared over 2. 3/30 seconds WL squared. All right, so that's cut 1. Now we can go about cut 2 exactly the same way. I could draw a little green squiggly on my FBD. I can start drawing my free body diagram of my cut. Again, I'm going to show W over the entire length of now L over 2, but my resultant then is going to be a function of that shorter length of W of L over 2. So my resultant is only W times L over 2. And it's going to act in the center of the distributed load. So at L over 4 from A or L over 4 from the cut end. Again, I'm showing my internal forces, shear, moment, and normal, and giving them all a subscript of 2 since this is cut 2. And I still have the external support reaction at A. That's visible in my cut, so I have my WL over 2. Again, we do our equations of equilibrium. Our normal force is 0. Our Y force in this case, when we sum forces in the Y, we determine that our shear is actually 0. The resultant and the AY cancel each other. And then if I sum moments at the cut, I'm going to find that the internal moment is WL squared over 8, still positive. And so we see it actually got bigger. So while the shear reduced as I moved across the length of the beam, it was higher at L over 4. The moment actually has increased between L over 4 and L over 2. All right, we got another cut to go. So now we can look at our third cut. And it's the same process. I'm going to draw my free body diagram. I'm still going to have W. Now my resultant is a function of the length of 3L over 4, which is how far away I've gone from A. And I'm going to have a resultant then of 3L over 4 times W. It's going to act at half of 3/4 L, so that would be 3/8 of L, both from A and from my cut. I still have to show the reaction at A, the WL over 2, and now I'm going to have my internal forces with the subscript 3, still drawn in the positive direction. When we write our equations of equilibrium and 3 continues to be 0, our normal force. This time, though, when I sum forces in the Y, I actually am going to get back out a negative answer. So my assumed direction of down, which is positive on that face, I got a negative answer, which means on that face it's going up, but internally it is still what we consider a negative shear. So there's negative shear acting at 3L over 4. So my shear value is continuing to decrease because I had positive WL over 4, then I had 0, and now I have negative WL over 4. When I continue and I sum my moments, what's going to happen is I had climbed from 3/32 WL squared to WL squared over 8, and I'm going to find that I've now decreased back down to 3/32 WL squared, but still a positive number. So this is kind of interesting because I'm seeing that these values vary depending where I'm at in the beam. And it might be really useful if I actually kind of made a plot. And I just said, okay, well, what do I have when x is equal to L over 4? Or what do I have when I have x is equal to L over 2? And I could make a plot. But of course, my plot would be more useful if I also knew my internal shears at 0 and at L. So we can quickly look at what's happening at, we could say x equal to 0 or x equal to L, and I can go back to my main free body diagram and I can draw x equal to 0 at A, and I can go ahead and now draw this free body diagram, and this for x equal to 0. And now this is a really interesting free body diagram because I'm showing a little nub of beam, but remember x is 0. So my distributed load W is a load per unit length. If it's, say, 10 pounds per foot, but I'm at x equal to 0, I've gone 0 feet. So I really have 0 load. The resultant would be W times 0 or 0. All right? So when I go to some forces in the Y, I just have the WL over 2 reaction at A and my shear, so my shear is just WL over 2. But when I go to take moments, the only thing that's there for moment is the the exposed internal moment, M sub naught, or M sub 0, since I'm at 0, and the WL over 2 times its moment arm to the cut. But if the cut's basically at 0 and WL over 2 acts at that point, it doesn't have a distance. Its distance is 0. So that tells me that the internal moment is 0, which sounds pretty good for a pin, because pins shouldn't have moments unless there were just an external moment applied. And we can do the same thing at x equal to L. And in this case, I'm saying x equal to L, but I'm going to make my L stop just before B, just before B. So I still show my internal shear moment and normal force. We're going to give them a subscript of L, saying we're at the end of the beam. I'm cutting just before that roller, so I don't see BY. But I can still write my resultant as W times L, and it acts at L over 2. I still have AY as WL over 2. So when I start doing my statics, I'm going to find that my shear is a negative WL over 2 for my internal shear at L. I'm going to find that my moment, just like at 0, it sums to 0. And again, no normal force. And so now we could go ahead and just draw a line where we mark 0, L over 4, L over 2, 3L over 4, and L, and put the shear values. And we can do the same thing for the moment, and this is what it would look like. And so what we're seeing is now I have this lovely plot. And from this plot, I can see that my shear varies linearly from a maximum positive WL over 2 down to a maximum negative of WL over 2 as I move from 0 to L. Which is kind of cool because since it's linear, if I wanted to know what was happening at L over 8, I wouldn't have to make a cut. I could just interpolate off of the chart, off of the plot. But when I go down to moment, I see that I start at 0, I jump to WL squared over 32, 3WL squared over 32. When I'm at L over 4, I go another L over 4, and I've increased to WL squared over 8, and then I start decreasing. And I decrease back down to the 3WL squared over 32 and then down to 0. And I can see that my changes aren't linear. In this case, they're parabolic. And if I had the equation of that curve, I could then just find out what the moment is at any point. But the cool thing is I can see the maximum moment is WL squared over 8. And knowing the maximum internal shear and the maximum internal moment is really key when you get into strength or mechanics of materials and you are trying to design your beams, and you have to know that information to do your beam design. And so what that leads us to, though, is that every beam is going to be different. Here we see, again, the distributed load that we spent the time calculating, but if we had done the exact same steps, made a cut basically at x equals 0, made a cut at L over 4, made a cut just before L over 2, and then another one just after L over 2 for this second beam where there's a point load at L over 2, a point load P, made our cut at 3L over 4, and then again at L, we could do the same thing and we could draw how the internal shear changes along the length and how the internal moment changes along the length for this given load. And what you might notice is if the load is constant, the shear diagram can be represented by one equation. I mean, look at our beam on the left with W. That load is constant. It doesn't change at all across the length. And so our shear diagram ends up also being represented by a constant line. It's constantly decreasing from WL over 2 to negative WL over 2. Our moment is also a constant curve. It starts at 0, it curves parabolically up to a maximum at L over 2, and then following the same parabolic curve, it drops back down to 0 at L. And so if we could write the equation of that curve, boom, we can do it in one equation. However, when we look at the beam on the right, where we just have the point load P, our load is not continuous along the length. We'd have the external reaction force, WL over 2, at the left end, or in this case, P over 2. We would just have a reaction at the pin vertically of P over 2, but then we have no load. We have no load from the pin to the middle. And then suddenly we have this point load where we drop by P, and then again, no load until we get to the roller. And we see that discontinuity. If the shear diagram, or if the load is not constant, we can see our shear diagram actually jumps at the change in the implied load. It actually jumps by the magnitude of the applied load because we went from P over 2 to minus P over 2. And the moment diagram also is discontinuous at the same point that the shear diagram is jumping. So we have a constant slope from 0 to PL over 4, but then it changes directions and we would need a new equation for that line. So what you should be taking away from this video is that we can make a whole lot of cuts along the length of our beam. And if we make a whole lot of cuts to calculate the internal shear and the internal moment for a given loading, we could actually come back and plot that. So we could look at the plot and immediately go, oh, well, at this value of L, what do I think the shear or moment is going to be? Or where along the length of my beam is the shear or the moment a maximum? But I would say that if we have to make too many cuts, what if we needed at L over 16 and then L over 8 and 3L over 16 and L over 4 and then 3L over 8? Like it could go on forever, right? What if instead we could make cuts as a function of X? So we could just say, hey, here's the moment as a function of X and put in any X value. Or here's an equation for the shear as a function of X and put in any X value. That would be a lot more efficient. It would be much less work, right? So we could be efficient. And we would just need a unique equation for every time the load changes. Because as we see on the plot on the right, our slopes and our equations for shear and moment are different to the left and the right of the P where the load changes. Take some time and think about this because we're going to jump right in. Or your next thing that you want to learn about is then how to write those equations as a function of X. Thanks for listening.